Good day, my name is Orevaoghene Ahia, and I am a research engineer at Insteadip. Today, my talk is centered on neural machine translation for low resource languages, where I'll be stressing on the importance of building machine translation models for low resource languages, especially African languages, and also running through a demo on how to build a machine translation model from English to Yoruba in Tensorflow. So low resource languages, what are they? Why do we call them low resource languages? Well, low resource languages are languages that lack large monolingual or parallel corpora resources that can be used to build NLP applications. So examples of NLP applications are Google Translate, which is a machine translation system, voice assistants like Alexa and dialogue systems, and all that. I'll continue my talk with a quote from the late Wangari Maathai. So Wangari Maathai was a renowned Kenyan political activist. She was also the first African woman to win a Nobel Prize. So she said that culture is coded wisdom and then it must be preserved. Language is one of the vehicles through which culture is transmitted, and we must preserve our languages for the sake of future and our present generations. Which leads me to my next point. How many languages do you think are spoken in the world? How many languages are spoken in Africa? How many languages are even spoken in Nigeria, even in our respective states? And then how many languages can we even speak ourselves? How many languages are we comfortable putting content? How many languages are we comfortable, or typically how comfortable or how bold are we in putting content in our local languages online? We have about 10,000 languages spoken in the world and up to 2,100 languages spoken in Africa. For the languages spoken in Africa, most of these languages are under-resourced or endangered and are sparse. We cannot find resources for these languages, or we can hardly find resources for these languages, which will create a barrier which will bar people from building technology or language technologies for these languages. Will the internet save majority of our languages or kill them? Many small languages lack an online presence, as only a handful of languages dominate the web. For instance, there is no African language that has more than 1% presence on the internet. We've grown up and we've been raised to only communicate in English, to only communicate in high resource languages. We've built technology for high resource languages because these are the resources that are readily available. Over 58.4% of the internet content is in English language, and whilst Nigerian languages such as Yoruba, Igbo account for less than 0.1% of internet content. Why is this so? This is a valuable question that we should be asking ourselves. Most of the technologies that are available today in the world are in English or other high resource languages. And this has barred people from accessing useful information or even using technology in general. It's evident that some low resource speakers do not have access to high-end devices. Some of them cannot even speak English, but are forced to learn English or other high resource languages just to be able to use these technologies that are available. I think I've come to understand that some people do not need to learn some English to conduct business. Some people do not need to learn English to be able to operate the tools or technologies they need on their farm. Some people do not need English language to run through some basic activities they need to do in their life. But then usually people are usually forced to learn the language because that is the only way they can access technology or they can access information. And this is not good enough. I think that we need to do better in terms of this. So this is one of the major reasons why we need machine translation. Because what if you had a software that could understand the language that you spoke and then would interpret that to another party in the language that he or she understands? Wouldn't that be great? Wouldn't it be nice to just type in your language and then the receiver or the other party understands what you're saying, talks back to you in the language he or she understands, and then that is interpreted, and then you guys can communicate well? Wouldn't it be amazing if we could boldly put out digital content in our local languages? Or when we see a tweet or an Instagram comment that it's not in your language, that you don't perfectly understand, and you hit the translate button on it, it gives you an accurate translation. I think that would be so cool. So my next slide, I talk about why we need, some of the reasons why we really need machine translation. Well, let's define machine translation. So machine translation is a field of computational linguistics that involves the use of computer software to convert natural language from one to another. So for instance, the example I have on the slide, we have two sentences which are translations of each other in Yoruba and Igbo. So the first sentence says Bawoni, and when I translate it, it is translated to Kedu Kai Mere. This is what machine translation, this is typically the intuition behind machine translation. It takes an input text as a source sentence from a user or from a person A, and then translates it into a target sentence for a person B. So here, Bawoni is my source sentence in Yoruba, and Kedu Kai Mere is the target sentence that it should be translated to in Igbo. So here I have other reasons why we need machine translation. Knowledge of many languages promotes intercultural dialogue and understanding. And this is very essential in a globalizing world. I said it earlier on, not everybody needs to learn English or high resource languages to be able to conduct businesses, to be able to get things done. People want to be able to use technology without having to worry about whether they understand English or whether they understand what they're reading. It also promotes inclusivity. If we have machine translation systems for low resource languages, it means that the technologies that will be built or technologies that are built will be accessible by a large number of people, right? We need to be more. It would ensure that people can access information when they need it in their languages. For instance, For instance, let's say there's sort of like a disaster somewhere, and then people need to communicate with the help services in their languages. But then these help services probably don't understand these languages, right? If we had a machine translation system, these people can flawlessly pass across their information and then get the right information from the help services. So we have cases like this where people cannot use technology, people cannot access information in some areas because they cannot speak English. It's also known that machine translation also promotes international trade. If this means that if we're able to push more, or if we're able to build more machine translation models for African languages, there's so much that we can change economically, and there's so much we can change. There's so much change we can bring that promotes inclusion. So in building machine translation models for African languages, usually when there is no resource for a task, people don't get to work on it. People don't see reason, someone doesn't see reason to build a pidgin translation system when there's no pidgin data. Someone doesn't see reason to build voice assistants in Igbo or something when there's no data. So this is where communities come in, and I'll be talking about how communities can help with this. So Masakani is a community of African NLP researchers that have been working to build NLP tools for different applications in low resource languages, African languages. Masakani is helping or working to build data sets and tools to facilitate NLP research on African languages also. I'm a member of Masakani, and we have a whole lot of other African members that have been working together to push NLP research in African languages. So one of the things that Masakani has done, because first of all, to train machine translation models or to train machine learning models, you need data, right? You need data to do all this. And then when there's no data, it's typically handicapped and then can't move forward. To address the lack of data, we have teamed up with, we've had people, or the beauty of Masakani is that there are people from different backgrounds. We have research engineers, we have machine learning engineers, we have people that have different experiences. So to address the lack of data, we've had people, volunteers, scrape the internet for digital content in African languages, or even help to create data sets, help to annotate African language data sets. Masakani has also helped to create benchmarks for 30 African languages, including Igbo, Yoruba, and Hausa, for machine translation. And this is something that has never been done before. Also, it's one thing to train your machine translation model, and it's another thing to actually see if it performs well. So another thing that Masakani has been able to do is human empty evaluation. So usually, when people who train machine translation models, they probably don't train it in languages that they understand. So sometimes you don't even know if your model is doing well, is doing a good job, except you have to get an external person that speaks the language and then can help you read through the translation from the model. But the beauty about Masakani is that we have people that understand these languages, training these models and evaluating these models. To join Masakani, the link to join Masakani is on the slide. And you can also reach out to me. You can follow Masakani on Twitter, Masakani NLP. Yeah, to contribute to our work and to join and support the work that we're doing. So aside from this, there are other works that have been done in this space, in the low resource space. So there's last year, I worked with a colleague of mine to build the first Pidgin unsupervised neural machine translation model. So from English to Pidgin. So unsupervised NMT simply means that we did not have parallel data. We only had monolingual data in Pidgin and in English. So to do this, we had to script data ourselves, prepare the data, process it, clean it into a sort of standardized NMT, neural machine translation data, and then train our model. And then over the last year, we've been able to get more data and also train supervised machine translation models in Pidgin. Another work that has been done at InstaDeep is this Arabic voice assistant. So voice assistant is typically an NLP application that helps you to get tasks done. So something like your Alexa or Siri, yeah, something like that, but in Arabic. Another amazing work that has been done in this the low resource space is this work on improving Yoruba diacritics restoration. It's an amazing amazing work that has been done by some amazing researchers, some in Masakani too. So it involves just improving the digital content in Yoruba, improving the way they're represented and the way they're put online. So we all, some of us know that Yoruba languages, for the Yoruba language, words have different meanings, and this is usually indicated with tonal marks. And usually when people put out Yoruba content online, they're usually missing their critics. And to get a very good machine translation model, due to the ambiguity of words in Yoruba, it's very important that words, Yoruba content contains their critics. So it's an amazing research that they've worked on and they're still working to improve. So here I have an example of an NMT model architecture. It's like the most common neural machine translation model architecture that people use to build translation models. So it's called the transformer network, and I won't be going into the details, but the intention behind it is that it has so it's like a sequence model. It has an encoder and a decoder. So encode means it takes in your source sentence. So for instance, now our input here is Bawoni, our source sentence is Bawoni, and then the goal is for it to decode, for the model to decode the source sentence into Kedu Kaimere. And I'll be talking more about this in my demo. So just to conclude, before I run through the translation notebook, I hope that we've seen that there is very important need to develop neural machine translation models for African languages, as this would definitely help with preserving and discovering of all these languages. We want people to be able to access technology. We want people to be able to use technology. We want people to be able to access information in their local languages. So it's high time we started building language technologies for them. And to achieve this, we need data. We need low resource data to be available. So that's the end. I'll just be going through the notebook for the demo. So here on this notebook, so it's neural machine translation from English to Yoruba. So the notebook trains the sequence model from English to Yoruba translation. And there's some assumption that you already understand the sequence models. So after training this model, we should be able to input an English sentence and return the Yoruba translation. And our translation quality might not be so good because first of all, we're trained with limited compute, and it's just a demo. So the first step is to import our relevant libraries and modules. So we're using TensorFlow here. So we're importing TensorFlow, Matplotlib, sklearn, Regix, OSIO These are just the relevant modules for preprocessing our data or translating our data. So after our imports, we download and prepare our data sets. We'll be using a language data set by JW300. So JW300, as you can see, is a parallel corpus of over 300 languages with around 100,000 parallel sentences per language. And this JW300 dataset is actually created out of the Jehovah's Witness tracts in many languages and was collected by some researchers into this. So JW300 has a lot of languages available. Like we saw there, they have 300 languages. But we'll be using the English to Yoruba data sets, which is relevant for this demo. So after obtaining our data set, I downloaded the data set and converted it from the XML format into just okay, I think this will take time to load, into just the normal readable text. So to prepare our data, as before inputting into our model, we add a start and end token to each sentence. So first off, we have a parallel data. So parallel data just means that you have a source sentence and the target translation of that source sentence in your data. So we add a start and end token to each sentence. This is to tell our model when a word or a sentence is starting. So if you have a start token in front of your sentence, it tells your model that this is the beginning of a sentence. And the end token tells your model that this is the end of that sentence. We would see what it looks like. So we'll clean the sentences and remove special characters, and we also create a word index, so we can map our words, our vocabulary. Vocabulary is simply the words in a set of words in your data set. Then we pad each sentence to a maximum length to enable us to pass into our our model. So here this is where the data is stored, here on my instance, and in the NMC data, train.yo is the Yoruba data and train.n is the English data. So this code is to pre-process the sentences using regex and also adding the start and the end token. So this is an example of an English sentence. Come here. And after pre-processing it, you can see that we have a start token before come and an end token before here. Also in the Yoruba sentence, wasibi, you have a start token before wa and an end token after b. So we clean our sentences and then we return word pairs. So word pairs, your source and your target sentence, the parallel translations. So we use this to open the data set and then split. So we split, like you have a document and you split it into sentences. Then we do our pre-processing for like a number of examples because data is very large. So this function is to create our data set. So creating our data set is just typically processing our data set from the so this is what the okay, let me open the Yoruba file. So this is what the English file looks like, and then once the Yoruba file loads, you see that it's a direct translation of the English file. So we pass our files into this function and then get the data set. So when we print out, so this is after processing. When we print out the last sentence, so this is what loving mother can ignore the sobbing of a child, and then the translation abiyamo wolo mari omo re ton sukun toju re agba. So after this, we tokenize our data. Tokenization is typically just breaking down text into smaller units. It could be you have a whole document and you want to break it down into sentences, or you have sentences and you want to break them down into words, or you even have a whole document and you want to break them down into words. You could also break them down into characters. So that's what tokenization does. And TensorFlow Keras has a pre-processing module that helps to do this effortlessly. So after, so we instantiate the tokenizer and then we fit it on our data. So we fit tokenizer on our data, and then we use this to transform our data and convert them into tensors. So tensors are what the model will understand. Typically, like numbers, values. We can pass in raw sentences into our data. That's why we go through all these processing steps in order to prepare the data. So after tokenizing, we now pad our data. So we pad all sentences to the maximum length of the sentence in our data sets. Then we return the tensors and the language tokenizer. So we pass this tokenize function into this load dataset function that helps us do the conversion and return the respective tensors of our source sentence, source language, target language, the tokenizers of our source language and our target language. So because of this, this is a demo. I limited the size of data sets to experiments. Actually, I limited it to 30,000 and not to 10,000 because transformer models are very large. Attention models rather are very large, and then it will take time to train like a large number of sentences. So this is where we So we load the data sets, get the maximum length of the targets of the tensors. Then we split our data. We know that to train machine learning models, we have to split our data into a train and the validation, and then a test set. So your train set is what you use to you use a train set to train the model, and then your validation to typically see how your model is doing on how your model is performing on another data that's not in the some other data that you use to tune your hyperparameters and see how your model is performing. So we use a train test split for model from sklearn, and then we split in the ratio. Typically our validation size is 0.2, so that's like 20% of the original data set, and then our trained data is 80%. So this is an instance of index to word mapping. So we typically collect the vocabulary of all, like the set of all the words in your data, and then create a vocabulary out of that, and then map. So this is just a sentence example to see how the tensors are represented in the data sets. So TensorFlow has different ways of passing data into your model. You can just pass them as NumPy arrays. You can wrap them with a TensorFlow dataset object, and so we'd first define some hyperparameters like the buffer size, the batch size, the steps per epoch, the embedding dimensions for model layers, the units for recurrent layers, and then the vocabulary, the size of our vocabulary for the source sentence, size of our vocabulary for the target sentence, and then we wrap all this with the TensorFlow data sets. Then now we write the encoder-decoder model. So we trying to implement an encoder-decoder model with attention, and you can read more about that in this TensorFlow neural machine translation tutorial. Here, the link is in the notebook, and so it's typically an encoder-decoder model that should take in an input sentence and decode a target sentence while paying attention to specific words or all the words in the sentences. So we subclass the Keras model and then define our encoder class, which batch size, number of encoding units, the size of our embedding layer, the gradient recurrence units layer. Then we instantiate the encoder. Then we move forward to the attention layer. We create a class for the attention layer that we create the class for the attention layer that actually determines how the model pays attention to specific words while decoding. Then we go on to the decoder layer that takes the input. So the decoder takes the output from the. If we go back to my slide here, the decoder takes the output from the encoder. So it takes the so what typically happens is that you pass in your source sentence, and then decoder has some layers, embedding layers, and some other things going on behind the scenes that produces a latent representation on the last encoder layer, and then this latent representation is passed into the decoder, which is passed on to until we're able to get our final output. So we have our decoder layer that takes the input from the representation from the encoder, and then decodes the target sentence. Then we define our optimizer and our loss function. Yeah, we're using the Adam optimizer and the sparse categorical cross entropy loss. That typically tells us how good our model is performing, kind of like the accuracy of our model while we're training it. So it's like a feedback that we get from our model. If we have a high loss, it means that our model is not doing good at all. And then this loss is derived from obtaining the difference between our target sentence, our target sentence, and then our original target sentence, and then the target sentence that the model outputs. After training our model, we're required to save the checkpoints to be able to use to do evaluations or deploy. So we create a directory to save our checkpoints, and yeah. So before we start to train, I'll just go through the training workflow again. So you pass in your inputs. So your inputs, your source sentence through the encoder, which returns the encoder output and the encoder hidden state. The encoder outputs the encoder representations. Then this encoder outputs and encoder hidden states and your decoder inputs. So your decoder input is the start token that is passed to your decoder. Then your decoder returns the predictions. So we're passing in the encoder representations into the decoder so that it can decode the predictions. So it decodes the predictions and the decoder hidden state. Then this decoder hidden state is now passed back into the model, and then we use the predictions to calculate the loss by comparing with the original sentence, the original target sentence. Then we use something called teacher forcing to decide the next input to the decoder. Teacher forcing is just a technique where your target word is passed as the next input into the decoder. So sort of like showing the model, sort of like some guidance for the model to be able to make good predictions or have some context on the predictions that it should be making. Then final step is to calculate the gradients and apply it to the optimizer and backpropagate. So that's all that's going on here. We use a custom training loop to achieve this. Use a custom training loop to achieve this, and yeah, we're ready to train. So here we train. You can train for longer. We can train for longer. We can train for a whole day. We can train for a larger number of epochs. But because of time, we're trained here for just 2 epochs. And yeah, at the end of the day, loss is not so bad. So after training the model for 2 epochs, and by the way, 2 epochs is very small to train a good model. So we want to use the model that we've trained to make translations. So the evaluate function that we have here is similar to the training loop, but we don't use teacher first in here. So the input to the decoder at each time step is the previous prediction that the model has made, along with the hidden state and the encoder output. So the model stops predicting when it predicts that end token that I mentioned earlier, and then it stores the attention weights for each time step. We need the attention weights to see where the model pays attention to when it makes predictions. So this is to plot the attention weights. So the way this evaluate works is that you want to pass in a new sentence into your models, you want to pass in a sentence for your models to make predictions for. So we run through the preprocess steps that we had run through before. You preprocess your data, convert them to tensors, and then pass them into the model to make predictions to evaluate. So this is function to plot attention, and this function is just to translate. So we get the latest checkpoint. So latest checkpoint is like the last checkpoint in the checkpoint directory. You can get whatever checkpoint you're interested in, whatever checkpoint you think had the best accuracy from your training. From your training logs, and then use that to make predictions. So note that this model was not trained for long, and it was trained with very small data due to compute. And so here we try to translate where is my place, and the model predicts Iboni Moshenshe. So at least the model tries to predict the first, is able to correctly translate the first two words. I know that the last three words do not make perfect sense, but the translation of where is in Yoruba is Iboni. So you can imagine if we're trained with more data and trained for longer, the model will most likely do better. And then if you look at this, so this plot is just to see what word the model is paying attention to when it's making predictions. And then here we can see that, so the plots with bright marks, have show that the model is paying so much attention to that area. So here we have yellow, so we can see that in this whole sentence, the model pays very much attention to where in decoding these predictions. So let's see another example. Here we translate why did Jesus cry. This is simply because the GW300 resource is in the religious domain. So I try to see if we can make good predictions based on the data, religious data. So why did Jesus cry? And then translation is Kini Iditi Jesu Shenshe. But then one important thing here to see is that the model is able to get like Kini Iditi Jesu. So the model is able to understand that Jesus means Jesu, and then Kini Di, why did. And then here we can see that the model still pays attention on the first word, why, and also pays attention on Jesus. So it pays attention on why and Jesus when decoding its predictions, and then it's fairly okay, given that we didn't train with so much data, and then we trained not for long. This is a very bad. The model translated this sentence very bad, and it's, here we have what would building the ark involve, and it says Kenya won't she. The model didn't get this well, and okay, this is another one. How does this reflect Jehovah's wisdom? Baoli Jehovah Shenshe. And yeah, the model tried and was able to. I've expected that There will be like a very bright activation on Jehovah's and Jehovah in this sentence. But here, so we can see that. So it will be amazing to try this. This demo and probably train it for longer with more compute, probably increase the number of the model size, the number of layers, the embedding size, and probably train with more data. Here we just have, like in the JW300, I think for everybody about 400,000 examples. So if I believe that if the model is trained for longer, we should be able to get better results than this. So this is why it's important to keep building tools for low resource NLP. Keep helping to build data sets for low resource NLP, and because if we have, you can see it yourself here. If we had more compared to the amount of data that we had, if we probably had more data set that we tried to train on, the results could have been better. And then usually in most researchers, when they train high resource models, they usually use data sets in billions and millions. Yeah, so if you look at the order of magnitude, it's quite even different from what we have for low resource languages. So this is the end of the talk. I hope you enjoyed the talk, and if you have any questions about the demo, about the data set, if you have any questions about Masakani, you can definitely reach out to me. You can definitely reach out to me on Twitter or through the GDG organizers. Or I'll be happy to answer any questions about InstaDeep, Masakani, or machine translation, or even low resource NLP, African NLP in general, or just even NLP. Thank you for watching this talk. Thank you for attending this talk. Yeah, bye.